Hello and welcome to my presentation for the SURE2009 research program. My research concerns modeling low-thrust orbital transfers using electric propulsion spacecraft technology. My work concerns modeling orbital transfers performed using a Hall thruster, which is a type of electric propulsion technology. This technology is divided into two main subsets, ion thrusters and Hall thrusters. The Hall thruster that I will be working with is a concentric Hall thruster, which I will describe in a moment. These electric propulsion thrusters are different from conventional rocket engines in that they accelerate gases through electric and magnetic fields to very high exhaust velocities. They're different from conventional chemical rocket engines in that an external energy source accelerates the propellant. This is unlike conventional engines where the energy of the propellant's own combustion accelerates the gases. Electric propulsion thrusters have very low thrust levels, generally less than 3 newtons, while conventional chemical rocket engines can produce over 1 meganewton of thrust in space. Also, while chemical engines can be used in the atmosphere or in the vacuum of space, electric propulsion can only be used in the vacuum of space. Electric propulsion is a relatively new spacecraft technology. It has not seen significant use since the last 10 to 15 years. But there are many advantages of low-thrust spacecraft technology. The high exhaust velocities of these thrusters allow for a very high specific impulse, which is a measure of the energy that can be delivered by the propellant for a certain amount of energy coming in to the propellant. They can achieve up to an order of magnitude greater specific impulse than chemical rocket engines, which is a great advantage when performing long-duration orbital transfers. This results in a mass savings from reduced propellant, which can either be used to launch on a less expensive and less capable launch vehicle, or can be used to extend the operational life of the spacecraft. The obvious drawback to low-thrust maneuvers is, of course, the much longer time required to perform them. One of the common orbital transfers performed on modern spacecraft is from a low Earth parking orbit, generally around 90 to 300 kilometers in altitude, up to a geostationary orbit, which is around 42,000 kilometers. In the conventional chemical rocket engine, an impulsive Hohmann transfer is used, which is an orbit that directly links the parking orbit to the outer geostationary orbit. This trip time is fixed due to the geometry of the orbit and is generally about 10.5 hours. A low-thrust transfer is a non-impulsive maneuver, which essentially means that the maneuver is, of course, performed over a long duration. This trip time is highly variable. It depends on the mass and the thrust level available from the thruster. Trip times of up to 1 year are possible. And although in this greater propulsive efficiency allows for much greater mass at the end of the life of the spacecraft, actually a greater amount of change of velocity is required for this non-impulsive maneuver, although the much greater efficiency of the thruster is able to offset this. I modeled these low-thrust maneuvers in MATLAB through a direct numerical integration of the equation of motion, which is seen here. It is a vector equation and can be decomposed into the Cartesian components. The guidance profiles for different segments that were performed, including inclination reduction and eccentricity reduction, were adapted from the work of a British scientist, Burt, who performed much of this work in the 1960s and is still used today as the basis for many more advanced types of transfers. One example of this transfer that was modeled is seen here. The different colors denote different segments of the overall mission. One of the more interesting concepts involving electric propulsion is that of the reusable transfer vehicle, which is essentially an upper stage of a rocket that remains on orbit and completes many different cycles of taking a payload spacecraft from a low Earth parking orbit out to geostationary orbit. This concept was first proposed by researchers at Edwards Air Force Base. This concept allows for various combinations of reusable components for this upper stage that is powered by electric propulsion. Some concepts have the solar cells and the power processing unit being the only units that remain on orbit, while what I studied involves the entire spacecraft, power delivery unit, thruster, and fuel tanks remaining on orbit. One of the main limitations of this concept is solar array degradation. Due to the natural radiation environment of space, solar cells experience a natural degradation. This does vary, however, with different types of solar cells. The collector arrays which essentially uses lenses to focus more sunlight on the arrays, offers significant radiation shielding. And over a long duration mission, typically up to a year, only 3% of this solar efficiency is lost by the arrays. A typical mission to geostationary orbit, such as I have been modeling, would involve placing the spacecraft in a 300-kilometer low Earth parking orbit. Thrust is then applied from the transfer vehicle perpendicular to the radius vector, which minimizes any losses due to opposing the force of gravity directly. Once the outer semi-major axis or size of the orbit is reached, the inclination is reduced from that of the parking orbit to 0, necessary for a geostationary orbit. And then the eccentricity is also reduced to 0, since a geostationary orbit requires a 0 eccentricity. The payload spacecraft is then released, and the transfer vehicle then increases its own inclination to match that of the parking orbit, then returns to the parking orbit to pick up another spacecraft. The concentric Hall thruster, which has not been tested yet, will be the later half of my research. This design uses two circular channels mounted concentrically, as the name implies, to accelerate ionized propellant. This offers several advantages, one of which is the area of the thruster itself on the spacecraft. Hall thrusters are surprisingly large given their thrust levels, and one of the main focuses of research is to reduce their area on the spacecraft. The Hall thruster offers much greater power per unit area, which also reduces the supporting mass of the structure on the spacecraft. This Hall thruster also promises to offer greater efficiency in different throttle settings, which is very critical for both the initial propagation out to a target orbit, as well as offsetting the orbital perturbations that affect any spacecraft in an orbit, which must of course be counteracted to remain in the target orbit. One of the big unknowns about a Hall thruster is how the two different channels will interact. It is not known if there will be interactions that enhance efficiency or degrade it, and my research will look at analyzing the performance to identify any such interactions. After this work is completed, I'll have a preliminary understanding of the basic concepts of efficiency of a Hall thruster and how it may be applied to orbiting spacecraft going to a variety of different target orbits. Thank you very much.